Welcome. The next topic that we are going to discuss is Poisson distribution. Again, here it is a Bernoulli trial that you will repeat it for any number of times. Okay, for any number of times in the sense it is repeated indefinitely. That is what we mean. Okay, this experiment is being carried out for infinite number of times. Here they are saying that it is the mass function of the random variable, and we can check whether it is a probability mass function. How do we check it? That is summation x runs from 0 to infinity e to the power minus lambda lambda to the power x upon x factorial. Okay, here this e to the power lambda is independent of x, so we just take them outside, and this is summation x runs from 0 to infinity lambda power x upon x factorial. We are very well able to see that it is the expansion of e to the power lambda, isn't it? So it is e to the power lambda that happens to be 1. So we have verified it as a probability mass function. Now we have a problem. If the number of accidents in a city on a day is a Poisson random variable with parameter lambda equals 3. Okay, find the probability that there will be more than two accidents. So more than two accidents it is given. So probability of x greater than 2. X greater than 2 means 3, 4, 5 till infinity we need to find out. Instead of doing it, it is better to do 1 minus probability of x less than or equals to. So that is at 0 and 1 and 2. Only these three things we find it out and subtract that one from 1. So we will get the required probability. Okay. And here we are given that x is x has a Poisson distribution such that this thing is happening, and we are asked to find out the mean and variance of the Poisson distribution and also find probability of x equals 1. But till now we haven't find out the mean and variance of Poisson distribution, isn't it? Okay, so for which let us try to evaluate the moment generating function of Poisson distribution. Okay, let me do here itself. So MGF, how do we achieve it? That is, m of t is expectation of e to the power tx. So here summation x runs from 0 to infinity. Initially in binomial distribution it was from x 0 to n. Now it is from x to 0 to infinity. E to the power tx and e to the power lambda power x upon x factorial. And again here this e to the power lambda is independent of x, so we take that outside, and this is summation x runs from 0 to infinity. If you see lambda e to the power, they both have the power x, so lambda e to the power t whole power x upon x factorial. Okay, what is it? Just like we have said that it is e to the power lambda, so it would be e to the power minus lambda here multiplied with e to the power lambda e to the power t. So it is e to the power, if we take lambda outside, it is e to the power t minus 1. So m of t is e to the power lambda multiplied with e to the power t minus 1. And what would be the derivative of it? So it is e to the power lambda e to the power t minus 1 multiplied with lambda e to the power t. Okay, and the second derivative is, okay, lambda is a constant, we take that outside, so we have uv. So let me have v as it is and differentiate this one, e to the power lambda e to the power t minus 1. So it is, again we'll have lambda e to the power t plus we keep this one, the first quantity as it is, and differentiate the second one. It is e to the power t itself. Okay, now what is mean? That is m first derivative at 0, which is same as that of expectation of x, which is, if you substitute here, okay, let me change the color. So if you substitute t equals 0, it is 1, 1 minus 1 is 0, so e to the power 0 is 1. Again here it is 1, so it is simply lambda. Okay, and e to the power x square, that is derivative of m, second derivative at 0. So here this lambda is outside, it is 1, it is again 1, it is 1, so lambda is left alone. Plus here it is 1, it is also 1. So it is simply 1, isn't it? So it is lambda square plus lambda. Now what we need is variance, that is sigma square, that is e to the power x square minus mu square, that is lambda square plus lambda minus lambda square, which is lambda itself. For this Poisson distribution, mean and variance both is lambda. Okay. uh, when we were studying binomial distribution, we said that if we write x as b of n comma p, it means that it is a binomial variate which takes two parameters. We need two parameters to describe the binomial distribution, whereas to describe the Poisson distribution we need only one parameter, that is lambda, which is the mean as well as the variance. Okay, now we can very well find it out, right? So it is given that 4 upon 7 p of x equals to, that is e to the power minus lambda, lambda square upon 2 factorial is same as that of 5 upon 9 e to the power minus lambda, lambda to the power 4 upon 4 factorial. Okay, so this e to the power lambda on both sides gets cancelled, right? And from this lambda upon lambda to the power 4 upon lambda square is same as that of 4 factorial upon 2 factorial, 4 upon 7 into 9 upon 5. Okay, so you get lambda square equals some quantity. If you just simplify it, you will get some value. From this you can reduce the value of lambda. Okay, once you know the lambda value, it is easy to find out p of x equals 1, isn't it? P of x equals 1 is e to the power minus lambda, lambda upon 1 factorial, right? So once you find lambda, things are done. Now here it is given that a monthly break. Okay, sorry. Yeah. So monthly breakdowns of a computer system is a random variable having Poisson distribution, and it is given that e of x square is 15. Okay. We are not given with either mean or variance. We are given with e of x square, which is 15. Okay. And we are asked to find out the probability that the computer will function for a month without breakdown with exactly one breakdown, which means p of x equals 0 and p of x equals 1 we need to find out. Okay, what is e of x squared? That is the second derivative of the mgf at 0, right? So what was it? It was lambda square plus lambda. So we have the information lambda square plus lambda equals 15. So it is a quadratic equation. You can solve the quadratic equation very well, and that gives you two different values. Okay, since it is a mean, it cannot be negative in this case, right? According to the experiment, we are saying that it cannot be negative because we are talking about the mean of the breakdowns. The breakdown is positive or 0. Okay, if there is no breakdown, it is 0. That may not happen in reality. So it should be positive quantity. This is the positive quantity. This is our lambda value. Substituting this lambda value into this and substituting x equals 0 and 1, we can very well find out the probability value, right? Okay. Here the next problem says that a car hire firm has two cars which it hires out day by day. Okay. The number of demands for a car on each day is distributed as a Poisson distribution with mean 1.5. It means what? Lambda equals 1.5. We'll have to calculate the proportion on each day on which neither car is used, which means 0. Right? When x equals 0, when small x is 0, what is the probability? Some demand is refused. Okay, so on an average it is 1.5. Okay, so if we are getting more than 1.5, we will have to refuse the demand, whereas the number of cars cannot be in fraction. So it means that till 1.5 we are able to manage, which means if it is 1 we can manage. If it is going more than 2 we cannot manage. We'll have to refuse some demand. So that is what we are calculating. Demand is more than 2 cars per day. In that case, we will say when x is more than 2, we'll have to refuse some demand. That this one like from 3 to infinity we'll have to calculate. Instead we'll calculate 1 minus probability of x less than or equals to, and we just do the calculation and see what are the probabilities. Okay, so here calculate the proportion that they are saying. From the probability you can very well find out the percentage. Just multiply it by 100, that gives you the percentage by which we get it. Okay, and now we will do something which is an interesting one. Okay, I told you guys that Poisson is an extension of binomial. In binomial, we repeat the trial for finite number of times, whereas in Poisson we do it for infinite number of times. That means indefinitely we are doing it. Okay. Now we can approximate Poisson distribution is the approximation of binomial distribution. That is what we are going to prove now. Okay, for which you just consider the binomial. Binomial is given in terms of n and p, that is ncx p to the power x q to the power n minus x, where x is running from 0 to n. Okay, we know that in binomial distribution, if we let n go to infinity, we will have to get Poisson distribution. That is what we are going to do now. Okay, this f of x, this ncx can be written as n factorial upon n minus x factorial multiplied with x factorial, and this p to the power x q to the power n minus x as it is. Okay, this one what I am doing is n factorial, I am splitting this as till n minus x minus 1, and I have this n minus x whole factorial as it is. Okay, so that it is upon n minus x factorial into x factorial and p to the power x and q to the power n minus x. So these two things gets cancelled. Now what is happening, just compare the results in Poisson and binomial. The mean is np in binomial, whereas it is lambda in Poisson, right? So therefore this p can be written as lambda upon n. Okay, so we are just doing it. Let np equals lambda, then what we get, p equals lambda upon n, and what would be q? It is 1 minus p, 1 minus lambda upon n. Therefore my f of x becomes what? So n times of n minus 1 till n minus x minus 1 upon x factorial. It is lambda upon n to the power x, 1 minus lambda upon n to the power n minus x. Okay, now this lambda power x, let me take it as outside, and this x factorial, let me take it as outside. Here this n to the power x is there, so I am trying to eliminate it. Okay, so n to the power x, from this I take n outside, from this also I take n outside, from all these quantities I am taking n outside. So in total 1 2, so when we have minus 1 it is n square. From minus 2 if we take that n out, from all the three terms if we take n out, it is n cube. So till x minus 1 we have, so x minus 1 plus 1, which means x. So n to the power x multiplied with 1, 1 minus 1 upon n till 1 minus x minus 1 upon n. Till this we have, isn't it? Okay, lambda to the power x we have taken out. So 1 minus lambda upon n to the power n, this minus x, let me bring it down. So this is what we have. So this n to the power x, n to the power x gets cancelled. Now let us take limit n approaches infinity to this f of x. What happens? It is independent of n, so it remains the same. Here 1 minus this quantity is 1. Again likewise still this quantity it is 1. So 1 minus 0 is 1 only. So from here we get 1 itself. This is, that is limit n approaches infinity, 1 minus x upon n to the power n is what? It is e to the power x. Okay, e to the power minus x, isn't it? If you have plus, it is plus x. So it is e to the power minus lambda, and here n is not present here. So only n of x here. This quantity becomes 0. So it is simply 1. So what we get is lambda to the power x e to the power minus lambda upon x factorial, which is the mass function of Poisson distribution, right? So moving further, we say when n is large and p is small enough, even though it is some binomial experiment, we can use Poisson. We can approximate it. We have a problem here that says that 5% of the items produced by a machine are defective. We are asked to find the probability that in a sample of 100 items, okay, produced by this machine, exactly two are defective. Okay, exactly two pieces are defective. That is what we need to find it out. Okay, using the formula for binomial distribution and the Poisson approximation to binomial distribution. So what you have to do here is, here n is 100, p is this one, and q is this one. Okay, you need to find it out. That is for this first case. So probability of x equals 2 means your n is 100 c2. Okay, 0.05 square, 0.95, 100 minus 2, which is 98. You need to calculate this probability. Okay, and in the case of Poisson, okay, lambda is what, that is np, we just calculated, and that happens to be 5. So e to the power lambda, e to the power minus lambda, e to the power minus 5, and 5 square upon 2 factorial, you just calculate it. Okay, compare on comparing these two gives you the almost equivalent probabilities. Since it was 100, it was fine. Okay, suppose you need to calculate x greater than 2, we'll have to work out too many things. Okay, that involves too much of calculations, whereas it is comparatively easier, right? And here if you see, it is given that if 0.2 percentage, 0.02 percentage of the people can get a bad reaction from an injection, find the probability that out of 1,000 people given this injection, at least 2 will have the bad reaction. Okay, here our probability p value is 0.02 percentage, which means 0.0002. This is the probability value, and n value is 1,000. Okay, so at least 2 means probability of x greater than or equals to, you will have to find it out. So it is 1 minus probability of x less than 2. We can write like this as well. So 1 minus probability of x equals 0 plus probability of x equals 1. If you are trying to do it by binomial, what happens? So 1,000, this is p value, therefore q would be what? Q would be 0.9998, isn't it? So this much difference are there. Like if you do it in that way, it consumes too much of calculation than this. Okay, we just approximate it as Poisson and perform it. That's it. Thank you.